Hello students, today we are going to continue with your topic thermodynamics and this is your third lecture. On your screen you can see the three figures in which first figure shows system and environment. System gains energy from the environment. This is because temperature of system is less than temperature of environment. Here Ts is the temperature of system, Te is the temperature of environment and Ts is less than Te. So in this case system gains the energy from surrounding. Here Q is the amount of energy transferred from environment to the system. In this case, we can consider this Q as a positive value, that is Q is greater than 0. In second case, in second figure, you can see that system is transferring its energy to the environment. It is because temperature of system is greater than the temperature of environment, that is Ts is greater than Te. In this case, system will lose its energy with the surrounding. So, amount of energy transferred from system to the environment, which is Q, we can consider it as a negative value. That is Q is less than 0. In third figure, you can clearly see that Ts is equal to Te, that is temperature of system is equal to the temperature of environment. So, system is in thermal equilibrium with its environment. So, in such a case, there will not be any transfer of energy from system to the environment or from environment to the system, which we have studied in the thermal equilibrium part. So, in this case, amount of energy transferred is equal to 0, that is Q is equal to 0, and this is the sign conventions that when system gains the energy, amount of energy transferred is positive, that is Q is greater than 0. When system loses energy, amount of energy transferred is negative, that is Q is less than 0. And when system is in equilibrium with its surrounding or environment, then amount of energy transferred is 0, that is Q is equal to 0. Now, in earlier lectures, you have studied what is meant by internal energy. Now, we are going to see here how we can change the internal energy of the system. Internal energy of the system can be changed by two ways. First, by heating the system. Second, by doing some work on the system. So, for that we are going to consider the experiment. The images of that experiment is shown in your screen. So, here the cylinder is provided with massless, movable and frictionless piston at its end and gas is enclosed in the cylinder. Now, in first image, you can clearly see that cylinder is in contact with burner. So, temperature difference between the source of heat, that is burner, and the system. System is what? Cylinder along with gas, cause heat flow. Due to this heat flow, temperature of gas inside the cylinder will get increase. Due to increase in temperature of gas, there will be the increment in the internal energy of the system or gas. So, you can now see the second image where we are pushing a piston quickly inside the cylinder. By pushing piston inside the cylinder, volume of gas will get decreased and gas gets compressed. So piston has done some work along the gas, against the gas. So gas gains the energy and temperature of gas will get increased. Along with this, internal energy of the system also get increased. So conclusion of this experiment leads us to very important principle of thermodynamics. Work done on or by the system and the change in internal energy of system are related through the energy that is transferred to or by the system, and heat is involved in the process. This leads us to the first law of thermodynamics. Now we are going to study the first law of thermodynamics. First law of thermodynamics shows us the relation in between work and heat. So first law of thermodynamics gives us relation in between heat and work. For understanding first law of thermodynamics, again we are going to consider an ideal gas enclosed within cylinder with movable, massless and frictionless piston. Gas is the system and cylinder along with the piston is an environment. So in first figure you can see that there is an expansion of gas takes place due to motion of piston outside the cylinder, or you can say towards the edges of cylinder. If gas expands, its volume also increases. How this happens? When molecules of gas strikes on the piston, it loses its momentum. That is, molecules of gas loses its momentum. Molecules of gas exerts pressure on the piston while striking on the piston. Piston move some finite distance towards the edges of cylinder. So gas does the positive work on the piston. In second image or figure you can see that piston is moving inside, or if you quickly push the piston inside, then gas inside the cylinder is get compressed and its volume will get decreased. So again, due to motion of piston inside the cylinder, molecules of gas strikes on the piston and gain some energy or momentum. Piston exert some pressure on the molecules of gas, and gas does negative work done on the piston. So in both the cases, when expansion of gas takes place, there is increment in the volume of the gas, and this is the positive work done. Work done is positive when volume of gas increases. Work done is negative when volume of gas decreases. Now we can consider same cylinder in which ideal gas is enclosed. Then cylinder is having A as a cross sectional area along with the piston, or you can say A is the cross sectional area of cylinder and piston. Now here we are going to consider P as a pressure which is constant throughout the experiment. The force which is exerted by the system on the piston is F is equal to P into A. you are knowing that pressure is equal to force upon area. Then by rearranging this equation, you can write force is equal to pressure into area. Now you can clearly see that here piston is going outside, means towards the edges of cylinder, means this is what positive work done. Now if gas is exerting very small force, then piston will move some smallest distance dx. Infinitesimal means what? A very small distance. Then work done by this force. Force कौन अप्लाई कर रहा है? गैस molecules on the piston. गैस molecules piston पे force अप्लाई कर रहे हैं. Due to that piston is moving towards the edges of the cylinder, and due to that force F is equal to P into A, there will be some work done on the piston by the molecules of gas, which is written as dW. Here piston is moving very small distance dx, that is why we can write work done, a small work done, as dW. Now you are knowing work done is equal to force into displacement. Here force is F is equal to P into A, and displacement of the piston, that is very small distance, that is dx. Now instead of F you can write PA in this equation, and dx is as it is. Now area into distance is equal to volume, that is why we can write P is dW is equal to P into dV. Now Vi is the initial volume of cylinder and Vf is the final volume of cylinder. Then we can calculate total work done by using integration. So dW, which we can consider as an integration of dW, is equal to W, which is equal to integration limits from Vi to Vf P into dV. Here volume of gas is changing and pressure of gas is constant. So we can take pressure of the gas outside the integration, and integration of dV is V, and by putting the limits you can write the equation W is equal to P into Vf minus Vi. Now we have seen this earlier also, that internal energy of the system can be changed by providing heat to the system or by doing some work on the system. So Q is the amount of heat added to the system, and system is not doing any work, then internal energy is increased by delta U is equal to Q. This means what? Delta U is the symbol of change in the internal energy. Now see in this figure, here if you are providing energy to this system, and the energy or heat which we are providing is only used for the increase, only used to increase the temperature of gas, not for doing work on the piston. So what will happen? That change in the internal energy of the system is equal to amount of heat added or provided to the system. So delta U is equal to Q. Now we can consider second case where system does some work to increase its volume. No heat is added to the system while expanding. So system will lose its energy to the surrounding and its internal energy decreases. Again consider same figure in which we are not providing any external energy in the form of heat to the system or to the gas. Then gas molecules are striking on the piston. Piston is moving outside or near to the edges of cylinder, but we are not providing any external energy. So what will happen? Molecules of gas will lose its energy with the piston or with the surrounding. So volume of gas is increasing, but there will not be any addition of external heat or energy to the system. So what will happen? Change in the internal energy of system is equal to minus W. It is because system loses its energy to the surrounding while doing some work. If system loses its energy, its internal energy gets decreased, and due to this we have written here delta U is equal to minus W. Means what? When system will do some work with the surrounding, internal energy will get decrease. Means when work done is positive, delta U is negative, and when work done is negative, then delta U is positive. So we can rewrite these two equations together, that one side of this, both the equations are delta U. So we can write delta U is equal to Q minus delta U is equal to Q minus W, or Q is equal to delta U plus W, and this is the first law of thermodynamics, which is the change in internal energy of the system is the difference between heat supplied to the system and the work done by the system on its surrounding or environment. That is, delta U is equal to Q minus W, or Q is equal to delta U plus W. Here Q is what? Amount of heat added to the system. Delta U, amount of increase in the internal energy or change in the internal energy. W is the lost in the energy or loss in the energy in the form of work done with the surrounding. So first law of thermodynamics is the extension of law of conservation of energy, or you can say generalization of law of conservation of energy. First law of thermodynamics is the extension of law of conservation of energy to systems which are not isolated. Isolated means what? It can transfer its energy or matter with the surrounding. The system which transfers or which is able to transfer its energy or matter with the surrounding. That is, system that can exchange energy with the surrounding. This exchange can be in the form of work and heat. So next 2 points are that thermodynamics does not help us to measure the internal energy of the system. We are concerned about change in internal energy after application of heat or work done on the system. So it is not needed to measure the internal energy of system, and we cannot measure it correctly. But what we require in thermodynamics, after application of heat or work done on the system, what will be the change in the internal energy, and that is required in terms of internal energy, not internal energy exactly. As we have seen earlier that Q, that is amount of heat added to the system, can be positive, negative or 0. Along with that, work done can be positive, negative or 0. So, change in the internal energy, that is delta U, can be positive, negative or 0, that is you can say unchanged. From these three figures below, you can get a clear idea about how change in internal energy of the system can be positive, negative or 0. So, in first image or figure, you can see that there is a system and environment where more heat is added to the system, that is Q is equal to 200 joule, and this work done by the system is 100 joule. Then with the help of first law of thermodynamics, you can calculate value of change in internal energy delta U. Then delta U is equal to Q minus W, that is 200 minus 100. You will get the 100 plus 100 joule as the change in internal energy, that is delta U is positive, that is delta U is greater than 0. In second figure, you can see that the amount of heat added to the system is less than work done by the system with the surrounding. So, delta U is equal to minus 200 minus 100. So, you will get change in internal energy of the system as minus 100 joule. So, here delta U is negative, that is less than 0. In last case or in last figure, the amount of heat added to the system is equal to the work done by the system, that is Q is equal to 200 joule and work done by the system is equal to 200 joule. So, delta U is equal to 200 minus 200, which is equal to 0, that is change in internal energy is equal to 0. So, internal energy of the system is unchanged. So, from these three examples, you can say that change in internal energy of the system can be positive, negative or 0, or you can say unchanged. Now, we can see what is meant by state variables. You are knowing that thermodynamics is not the study of changes in temperature of the system only. Along with temperature, system gains or release energy and other properties of system also changes. To understand these properties, we defined system variables. Now, as I have told you, when temperature of system changes, its other properties also changes. For example, pressure, volume, density, mass, etc. These are the macroscopic properties of the system. When system is in equilibrium, any observable or measurable property of the system is called the state variable. Now, we can see what is meant by intensive and extensive variables. Intensive variables are those variables which does not depend on the size of the system, just like pressure, temperature and density. And extensive variables are those variables which depends on the size of the system, just like mass, volume and internal energy. Now we will study what is meant by thermodynamic equilibrium. The system is said to be in thermodynamic equilibrium when condition of equilibrium is satisfied simultaneously. Just like that, the system in which thermodynamic equilibrium is there means system is in mechanical equilibrium, chemical equilibrium and thermal equilibrium. So, what is meant by mechanical equilibrium? So, as you can see the two images on your screen, in one first image or figure you can see a seesaw and second a pulley where two masses M1 and M2 and A and P both are same, or you can say the force or net force acting on that seesaw is equal to 0. That is why that seesaw is not moving up and down. Just like that, in pulley, the net force acting on the pulley is equal. That is, gravitational force due to masses A and B is equal to the tension T1 and T2 in the string. And due to these two forces have get balanced, pulley is not moving. It is stable. So, what is meant by mechanical equilibrium? Net force between system and surrounding as well as within the system is 0. That is, summation of F is equal to 0. Then we can say that this is the condition of mechanical equilibrium. Again, pressure throughout the system and between the system and surrounding is same. Just like that, just like force, pressure throughout the system, between the system and the surrounding should be same. Means that particle or object on which the forces are acting or pressure is applied, if summation of all will be equal summation of all will be 0, then that system is said to be in the mechanical equilibrium. Now we can see what is meant by chemical equilibrium. So in chemical equilibrium, no chemical reaction is going on in the system. No diffusion, no transfer of matter, and whatever the chemical composition which is present in that system will not change with the time. This is called as chemical equilibrium. Thermal equilibrium you have studied earlier, but for the information I can read it again. Temperature of the system is uniform throughout. Two substances or system reach to the stage where there is no transfer of heat, and this is called as thermal equilibrium. This is all about your third lecture. In next lecture, we will start with the thermodynamic state variables and equation of states. Thank you.